Okay, so for the last talk today, we're with Tim and Moritz talking about the next generation of virtualization-based obfuscator. So please give a warm welcome to Tim and Moritz.
Hi guys, thank you. Great to be here again. So today we will talk about the next generation of virtualization-based obfuscators. So I'm Tim, I'm the co-founder of Mproof, and for my main time I design software protections for deeply embedded devices, and I'm also a trainer. This is my co-speaker, Moritz. He is a final year PhD student at the Ruhr-Universität in Bochum. He's working on bug triaging, but also did quite a lot in code deobfuscation and deobfuscation. Okay, so, that's better. So, okay. Today, we talk about three different things. First, VM-based obfuscation, then how to break them, and then we talk about new developments in this area, basically the next generation. So, let us begin. First, why? Well, obfuscation is used quite a lot to complicate reverse engineering attempts. So it is used to protect intellectual property, but also to protect malicious payloads. It is pretty common in DRM systems everywhere. In your browser, in your mobile phone, in your kernel. And one of the most sophisticated obfuscation schemes is virtualization-based obfuscation. So think about, we have a piece of code which we want to protect. So if we wouldn't protect it, we can just look at it in IDA and reconstruct it. So to obfuscate that, we basically first retranslate this piece of instruction sequence in a made-up instruction set, like something in a virtual machine that just has a custom instruction set architecture, and we just rewrite the code in this new VM. And on binary level, this is more or less some bytecode, which is then interpreted by a VM. So on the binary level, it looks like a sequence of random bytes. And on the code level, we push the bytecode and then call the VM entry. If we now want to analyze or reverse engineer the obfuscated code, we look at a random sequence of bytes, which doesn't make any sense for us. Well, we can't disassemble it, we don't understand it, we don't even know if it's code or data, since it's just something which your IDA doesn't know. So, virtual machines can be understood somehow as some function-like constructs which do some obfuscation. Similar to functions which have a prologue and an epilogue, a VM has an entry and an exit. If we leave the native CPU state and switch into the VM state, we have to do a VM entry, which basically backups all the native CPU registers, initializes the VM, the keys, and stuff like that, and then transfers the control flow to the VM itself. Once we've done all the calculations, we leave the VM exit, which is the function epilogue, where we restore the outer CPU context. Then we have the VM dispatcher. The VM dispatcher is the fetch, decode, execute loop of this interpreter. It basically reads or fetches some bytes from the bytecode and decodes the instruction. Then it forwards the virtual instruction pointer. It looks up the handler, the opcode for the handler table, and directs the control flow to the handler. The handler itself is some implementation of the virtual instruction set, like it performs an addition, a multiplication, or an XOR, or something like that. So we basically invoke the handler. Typically, there are a few hundred handlers in a VM, and these handlers are stored in a central data structure, which is called the handler table. The handler table is an array of function pointers, where basically all the handlers, all the VM semantics are included. If we have a look at an older version of VM Protect, we can basically do a one-to-one mapping. So initially, we have the VM entry, which prepares the virtual machine. Then we jump to the fetch, decode, execute loop, which reads some part of the bytecode, knows which handler to jump, directs the control flow to the handler, performs its handler calculation, the handler jumps back to the loop, and so on, until at one point we direct the control flow to the VM exit, restore the outer state, and leave the VM. To give you one example, here we have a VM dispatcher where RSI is the virtual instruction pointer. We read from it, we increment it, and then we guide the control flow into RIX and jump to the handler table. An example handler of VM protect, a stack-based machine, is, for instance, we read two values, perform a logical NOR, and write back the result, and then we jump back to the dispatcher. So if we have a simple VM like that, how do we reconstruct the original code? Well, remember, the bytecode itself is the original code we want to reconstruct. So we basically want to write a disassembler for the bytecode. But to do so, we first have to understand the VM architecture and the context. Is this a register-based machine or stack-based machine? Where's the virtual instruction pointer? Where's the stack pointer? Afterward, we have to reverse engineer the individual handler semantics. What's an addition? Where's an XOR and stuff like that? But also, how does the instruction encoding look like? After we have all this information, we can write a disassembler for the bytecode. Then it takes as input the bytecode from the data section and just disassembles everything. Then we basically have some kind of VM disassembler output, which we then can use to reconstruct the control flow and afterward reconstruct the high-level code. So think about the following instruction encoding, where we have an opcode, a register, and a register. And think about we have this sequence of bytes. So disassembler would take the first byte, say this is an addition. The second byte is encoded in a register, R1, and the second byte, register R2. The fourth byte is multiplication with R1 and R5. Once we have our disassembler output, we then can start with reconstructing the high-level code. In this case, it would be R1 plus R2 times R5. So these VMs are relatively simple. However, most modern VMs, like VM Protect or Temida, have a few hardening techniques which make it a bit more complicated. So first, think about, we have an individual VM handler, and it performs usually a simple operation, like an addition or multiplication. So they are conceptually simple. What's typically done is that you artificially increase its complexity by using traditional code obfuscation techniques, like opaque predicates, junk code, substitution, and stuff like that. The second thing you do is you basically duplicate the handler. So instead of having a single handler which performs an addition, we have 100 or 500 handlers which perform additions. The goal is here basically to manually increase the workload of the reverse engineer by increasing the number of handlers a reverse engineer has to look at. Typically, current VMs deploy between 2 and 8,000 handlers. So to visualize that, we have this handler table, and then it might look like that. We have several copies of the handler, and all of them look a bit different because they are obfuscated with some different opaque predicates or stuff like that. So now we have more handlers and more complicated handlers. Now we want to get rid of all the central data structures. So having a central dispatcher has the problem that we can use it as a single point of failure to observe all the control flow between the different handlers. Therefore, what's typically done is that we don't jump back to one central dispatcher. Instead, we inline the dispatcher at the end of each handler, and then one handler directs the control flow to the other handler without going to a central instance. So, and this is a technique that goes back to the 70s and is known as threaded code. The fourth technique is basically to kill also the handler table. The handler table is an array of instruction pointer and function pointers which reveal all of the handlers in the VM. However, what we would like to do is to hide the location of handlers which have not been yet executed. What you do there is basically you extend the bytecode by putting, instead of opcode, op0, op1, you extend it by the jump offset to the next handler address. And then the inline dispatcher basically reads it and jumps to that. And this is also an optimization technique which goes back to the 80s and is known as direct threaded code. So now we don't have any central data structure and we have more complicated handlers. However, we do one more hardening technique, which is one of the strongest ones. It is called as bytecode blinding. Up until now, we were able to reverse engineer each handler on its own. We were able to reverse engineer the instruction encoding and so on. And then we can just dump the bytecode from the data section and write a disassembler for that. However, now we start to encrypt the bytecode. If the bytecode is encrypted, our disassembler wouldn't work. We first have to get the decryption key such that we can decrypt the bytecode, such that our disassembler would work. However, the decryption key isn't a static key, which is just used all over the place. It's more like built in a control flow sensitive way. So it's built in a way that the VM entry initializes the key. The first handler which is executed then decrypts with another key, the next handler, which again decrypts with another key, the next handler, and so on. In other words, the encryption itself is built in a way such that it is control flow sensitive. To decrypt the bytecode, you have to follow the VM execution flow from the start to the end. And this basically enforces you to do a global analysis of the bytecode and prevents you from some local patching. So if we have a handler which looks like that, like we have an operand, we have a VM context where we basically perform some semantics operations like an addition or multiplication, and then we jump to the next handler. Now we add some dedicated decryption routines. The operand we read from the bytecode is encrypted, and we decrypt it with a key. We update the key, we perform the semantics operations, we fetch the next handler in an encrypted form, we decrypt it, and then we update the key again. So decryption itself is not real magic, it's more an XOR with a constant or something like that. But still, giving its control flow sensitive nature, it's hard to bypass in general. So if we want to deal with these hardened VMs, what we have to do is we have to first locate the VM entry and the bytecode. Then we have to simplify the handlers with a lot of different program analysis techniques. Some of them we will see in a few minutes. And once we have done that, we basically have to write a control flow sensitive disassembler which follows the VM execution flow from VM entry to exit and dumps the the decrypted VM bytecode on the fly. And then we can use this output and reconstruct the high-level code. So what kind of automated attacks are there that we can use on VMs? One of them is instruction removal. Instruction removal basically has the goal to remove unnecessary or bloat instructions. So many handlers, like VM product optimizer, use a lot of junk code, which can be easily removed by compiler optimizations. Think about, we have the following code. If you have a look at the highlighted instructions, the first one, the EAX, is basically dead since it just overwrites EAX in the next instruction. Also, move ECX doesn't do anything meaningful, and adding 0 to a register also doesn't so we can just delete them. Something like that is called dead code elimination. After we did the dead code elimination, we can proceed further. So think about, we have a constant which we move into a register, and we add to this constant another constant. What we could do instead is delete the first instruction, calculate the real constant at compile time and move it into EAX. Something like that is called constant folding. And finally, we have something like we move a constant to a register and a register to another register. We could just move the constant into the final register, and this is called constant propagation. So once we cleaned up this a bit, we have some instructions left. The push and pop EAX are not required anymore since we don't modify EAX anywhere. Same for not EAX, this doesn't do anything, we can just delete it. So, and we come up with that. Those optimizations are called peephole optimization, and in the end, we got a cleaned up instruction sequence. If we have a Temida handler, which looks like that, and we employ different code compiler optimizations, it will afterward look like that. And remember the structure of the handler we've seen before. We can now easily see where's the decoding, where's the blinding, where's the semantics, the addition, the subtraction, and where's the inline dispatcher. To go one step further, there are even approaches which basically take the binary, lift the binary to an intermediate representation, like LLVM IR, then use the compiler optimizations to clean up a lot of mess and compile it back to some binary. So usually this binary cannot be executed then. However, it can be loaded in IDA and can be analyzed way easier. Besides instruction removal, there's also another technique which is called symbolic execution. Symbolic execution is some kind of computer algebra system for assembly code. Think about the following handler on the left. We start by moving some instruction RBP into RCX. Second, we move the memory cell of RBP plus 4 to RBX. Then we perform a NOT. Since we know that RCX is the memory cell RBP, we can just propagate the NOT to the input. And the same with RBX. Now it gets a bit more interesting. We do a logical AND. But we can propagate the values such that we have not RBP and not RBP plus 4. Think about the symbolic execution engine has some kind of simplification. Like it can detect this pattern and simplify it with some easier representation, like this logical NOR. And then we propagate this one to RBX plus 4. We take care of the flex, we take care of the pop, and we jump back to the dispatcher. In the end, this whole symbolic execution engine gives us, besides others, that this symbolic summary that we have RBP plus 4 equals RBP nor RBP plus 4. Basically, we derived a symbolic formula for the core semantics. There's another approach which doesn't look at the code itself, which is more based on the semantic behavior of the code, which is called program synthesis. So what we use is we use the code just as the black box and do some random I/O sampling. We generate some inputs, we execute the code as an oracle and observe its output. We do it a few times and get some I/O representation which just maps different inputs to different outputs. And then we use some kind of learning which basically learns a similar function which has exactly the same I/O behavior. So in this case, we might learn x plus y plus z. So remember, instruction semantics are conceptually really easy. It's an addition, it's a multiplication, and stuff like that. So therefore, we can also do a lighter synthesis approach, which is known as codebook attacks. What we do is basically we generate a table of predictable instruction semantics, like addition, multiplication, subtraction, and so on. And then we pre-compute a lookup table, which basically takes the input-output behavior of those VM ISA instructions and maps I/O behavior to the handler. And then we can just symbolically execute an obfuscated handler, I/O sample it, and look up the result in the lookup table. And once we find something, which is easier, it's like we find that it's an addition, we can use SMT solver to prove the semantic equivalence of our lookup table entry and the symbolic formula to check if we really did calculate it the same. And if so, we basically, we got the handler's core semantics. So to conclude the attack surface, we basically have some shortcomings of current VMs. One of the shortcomings is that we have a predictable instruction semantics with meaningful mnemonics. This basically means two things. First, they are vulnerable to synthesis-based attacks since semantic is simple. And second, they enable writing disassemblers because they have something like citizen addition or multiplication or something like that. The second drawback of such VMs is that VM components are independent of each other, which means that the obfuscation is mostly local. We can have a look at a simple handler, at a single handler, and extract its core semantics by just doing some analysis. So we basically can look at all the handlers independent from each other, and we can extract the core semantics. So basically, to summarize the VM attack landscape, we have instruction removal, symbolic execution, and program synthesis, and in static and dynamic scenarios, and current VMs are just vulnerable to all of these attacks. However, there's something happening in the last months or years. So there's a new VM rising on the horizon, new generation of VMs, which also can be partially found somewhere in the wild, which basically follow new concepts. So the design goals are mainly that they withstand all of these attacks. And if we generalize it a bit, there are mainly two reasons, two design principles, which cause this resistance against those attacks. And now we will take a look at it. The first one is basically complex and target-specific instruction sets. So instead of having instructions which perform an addition or multiplication, or having a fixed instruction set, like if you have a look at 10 different VM protect samples, all of them have the exact same instruction set architecture. So instead of doing it like that, we now build instruction set architectures based on the target specific, based on the input target that we want to obfuscate. So in other words, we generate handler semantics are based on instruction sequences from the original target program. It doesn't matter if it's a basic block, a partial basic block, a whole function, or stuff like that, but we take arbitrary sequences from a semantic level and put them into dedicated handlers. And we don't only do this for the addition or stuff like that, we do it in a way such that they are really, really complex. Complex means they do a longer sequence of semantics, such that we have first a lot of diversity, and second, they are complex enough from a semantic point of view that they provide resilience against synthesis-based attacks. And they can also be constructed in a way that they are data flow dependent. We will see later what this means. So basically, this design principle makes it possible that synthesis-based attacks do not longer work, but also that we cannot create any meaningful instruction mnemonics for the VM disassembler. So we can't say this handler performs an addition or this handler performs a multiplication. We would have to say this handler performs an addition, multiplication, XOR, sub, and a multiplication at the same time in a row. So having something like that isn't really this convenient for disassembler. For writing disassemblers. Besides making the handler semantics target-dependent and more complex, the other design principle is basically to combine or interlock different VM components in a way such that you can't analyze them individually. So in other words, you have to enforce a cross-handler analysis. And this can be done in various ways. Let me just discuss some of them. One of them is that you could encode them mathematically via arithmetic encodings or mixed Boolean arithmetic, such that one handler performs some encoding, the other handler in the execution flow performs some operations on that, the other handler encodes a bit more, and just 10 handler somewhere in the future decodes the stuff. So basically building a chain of arithmetic encodings such that you only learn what's going on if you analyze different handlers in a row, in the correct row. This can be understood as some generalization of bytecode blinding, where you don't encrypt the bytecode in a context-sensitive way, but also encode the instruction semantics in a context-sensitive way. The second thing is that you could build opaque predicates, which are data flow dependent or even multi-threaded. So as obfuscator, you basically know which handler will be executed before the other handler. And therefore, you could build, if handler A is executed before handler B, you could insert some opaque predicate in handler B, which doesn't look like an opaque predicate if you only look at handler B. Instead, you have to look at handler A before, which enables some global flag, which relies on handler B. So if we execute handler A before handler B, it becomes an opaque predicate, and it doesn't otherwise. Another thing is merged handler semantics. We could take different handler semantics and merge them into one large handler. So however you do this, the thing is you are basically enforced to do some global analysis instead of some local analysis. So in other words, the analysis effort rises enormously, since you don't know where's your analysis window. Normally, you have to start at the VM end, you have to start at the handler begin and end at the handler end, but now you have perhaps a look at the whole VM execution, or just as a handler slice of different handlers in a row. So you don't know. And the other thing is that analysis tools reach their limits, since it's possible that we operate on thousands of instructions at the same time in a row, that we have to keep in memory, that we have to analyze, and stuff like that. And usually, tools go out of memory or take a long time to process these things. So, to conclude, we basically have two design principles, which makes current VM and the next generation of VMs way harder. The first is we make target-specific instruction handlers, and the second is we enforce a global analysis by interlocking VM components. And now I will direct the talk flow to Moritz, who will basically talk about Loki, a project of us, and will talk about how one of these next-gen prototypes may look like.
Thank you very much, Tim. Hello, Montreal. So I'm excited to talk about Loki, as Tim just said, which implements these design principles. The first thing I'd like to get out of the way is that Loki is an academic prototype of such a next generation VM. And as with all academic things, there's a paper. So if you're interested in that stuff, you can check out the paper on arXiv. The paper will be published on Usenix later this year. But I'd like to stress that it's not only an academic thing, so it's not an academic bubble talk here, but you can find this shift towards such designs in industry. So let me quickly give a shout out to all the co-authors which have helped working on the paper and thus also have contributed to this talk. Thanks to you folks. Before we dive in. All right, so you remember this instruction encoding, which Tim has shown you earlier, right? And when speaking about the disassembler. So we have add and mul, and for the sake of this talk, or for the rest, we will consider them as mathematical functions, right? It should be easy to see that they are doing the same thing. And the other thing I'd like to get out of the way right now is how we will deal with constants. So there's the constant 0xff in the here in the instruction, and we will extend the instruction encoding to account for that, and consistently with that also the handlers. Okay. All right, so the handlers can be represented as functions, which we will do. And when I say instruction semantics in the following, I refer to the handler's actual computation. All right, so with that we are set, and we do note, as Tim has outlined also before, that these VM handlers are quite simple and they are broken in their current state of affairs. So the question is, can we do better? And yes, we can, as we will see. So the very first thing we can do to make our handlers better is we can merge instruction semantics. So we pick two handlers and we merge the instruction semantics in a new handler. And to do that, we need another variable, so the key k, which facilitates the selection of the instruction semantics we'd like to execute. Now, with these key-dependent instruction semantics, we can do great stuff. So if we consider a control flow graph representation of this, there's the if. And based on the if, you can go either down one of two routes, right? But that's not what we want. We want one large basic block where all the instructions are in there. And we can actually get there pretty easily, with a polynomial encoding. So these two are equal. However, one has the if in it, and the other uses here a multiplication and an addition to combine the instruction semantics. So as you can see, if the key is 0 for the first check, it will be 1 multiplied with x plus y. If, however, the key is not 0, it will be 0, and it will not affect the total computation. Okay? So this leads to a tight interlocking of individual instruction semantics. And already with this interlocking of instruction semantics, we do kind of better. So we are protected against the removal of instructions, and we make the whole thing a little bit more complex, which helps against symbolic execution. So it's easy to see that these key checks are currently very simple, right? It's a simple comparison. And what I brought you here is we can do better than a simple comparison. We can use some hard problems, and there's two of them I want to present to you. So the first one is factorization. So the question we are asking is whether our key k is a factor of some number n. And the second, similarly difficult, is quadratic residues, where we ask whether k to the power of 2 is equal to q modulo m. So doing this is great because now SMT solvers will be stalled. So there's no partial solutions for these problems, and there's just one correct solution, and it's not easy to guess, which makes SMT solvers stall out. And stalling out SMT solvers is helpful because Tim has presented you these codebook checks where people use SMT solvers to compare what is actually happening in there, right? So we check whether it's doing x plus y, for example. And there's another key encoding I'd like to introduce. So instead of using only these mathematical type of problems, we can get rid of the quadratic residues. We've never liked them anyway. And we use a partial point function. So one example of a partial point function is this. That's synthesized. And we impose two constraints on these point functions. Constraint number one is that for a valid key, so for example, for OX1336, it returns 1. This means we've selected this instruction semantics, and we want this result. And the second constraint is that for the key of the other instruction semantics, it returns 0. Remember, this is required such that we can actually select the other instruction semantics as well. So the neat thing is, it's defined exactly for these two valid keys. But for all other values of k, there's just some random garbage coming out, right? That's not helping when you're putting in random values. And guess who's putting in more or less random values? It's I/O sampling, which you do for synthesis. So if you're just putting in random values of k, you won't get far here, which is great because these both key encodings, so the SMT hard key encodings and the point functions, provide us protection. So we can stall out, most importantly, program synthesis that is static, So the dynamic scenario doesn't work out, right? So if you're a dynamic attacker, you can see all keys at runtime. You already know which keys to put in, and you can do I/O sampling. And it provides some protection in regard to the removal of instruction and symbolic execution, because we make the key check significantly more complex. All right, so there's still the dynamic attacker for the program synthesis, the dynamic scenario. Can we protect against that? Yeah. So what we are going to do is we pick our instruction semantics and we replace it by something that's semantically more complex. So that's the target-specific part Tim was getting at you before. We can do it for the other one as well. So instead of having x plus y, we have, for example, x plus y plus x, which is a simple example for that. So the gist is that we have semantically complex arithmetic operations, and the first question I'd ask myself here is, how do we get here? And for that, I brought you a small assembly snippet on the left side, and on the right side, it's the same in SSA form, so single static assignment, where basically each variable is unique. And what we are going to do is we recursively replace uses, so where the variable is used on the right-hand side, with their definitions. Let me walk you through a small example. So for example, the last variable ADX3 is defined as ADX2 multiplied with 0x10. And we're going to look up the definition, so ADX2, and we slice in this definition. So the result is ADX1 plus ECX1 multiplied with 0x10. So by this first lookup, we extended here from having one operation to two, making it more complex. And you could go on like that, but we won't do that for here. In our mathematical function representation, we can handle it like that. So that's x plus y multiplied with c. All right, so these semantically complex operations based on the actual target program are great because synthesis is really good for simple operations. So for simple operations, you can synthesize them without problems, but if it gets complicated, it won't work. So this stalls our program synthesis, and the inherent complexity of these expressions also makes symbolic execution less of a threat. So still, symbolic execution, we haven't tackled that explicitly, so we do that now. And what we do is we pick our instruction semantics and we replace it by an equal but significantly more complex, syntactically more complex expression. We can do that with the other one. These syntactically complex expressions are usually created using so-called mixed Boolean, or MBA for short, arithmetic. So let me show how that works. So we do have the instruction semantics on the left side, and we, for example, pick a small sub-expression here, which we want to use the MBA on. And on the right side of the slide, you do see the rewriting rules. So we have a number of rewriting rules, where for each rewriting rule, we have this small, simple expression on the left-hand side and an equal but more complex expression, syntactically more complex expression on the right side. So what we are going to do is we look that up in the rewriting rules and we just insert it, right? And the neat thing is these two expressions do exactly the same as before. So we have not touched the semantics anything. So and that's how you traditionally applied MBAs. We were done. I'd like to point to two things here, which is why this isn't great. So the first thing is we do have 47 rewriting rules. That's not a lot, right? Why can't we do better? Because mostly people crafted these rules by hand. So you came up with a clever representation and you noticed, oh, it's doing the same, and that's a new rewriting rule. So what we've been doing is we've used enumerative program synthesis to just create every expression up to a certain depth and check for equivalence. And this gave us a large lookup table of rewriting expressions. So I'd say it's fair to expect that in future we will deal with these large lookup tables with all identities or with all rewriting rules up to a certain depth. And the second thing is, why stop here? Why apply one rewriting rule and be done with it, right? So what's more powerful is recursive approach, right? So we'll move our rewritten expression up there. We pick another sub-expression, we look that one up, and we place it in there. And it's still equal. It's the same as before, right? And we can continue like that, right? Pick another one, look that up. We can go on like that all day, making this from a very small expression to a very large one. But for now, we stay at these three insertions. So this recursive rewriting is great, but there's another type of MBAs that's great as well, so-called polynomial MBAs. The situation is, again, that we want to here pick a sub-expression from our instruction semantics and rewrite it. What we use here is, instead of these lookup tables, we are going for a function pair, so a function that has an invertible function that inverts it. And for example, this is one example for that. And using those, we have the equal expression, but a more complex one, right? It's important that this particular function is valid on 1 byte, so in 1 byte variables. Okay, so this plays out like that. We want to replace the sub-expression by the function, and it's in the invertible. So we look that up, raise it, and do the same here, and we get that. So this is the gist of polynomial MBAs, and there's nothing stopping you from having simple polynomials. You can go to higher orders, whatever you desire. So the problem here is you need this function pair, right? So you need the function and the invertible function, but you still get this equal representation, but significantly syntactically more complex one, right? So people working on finding such functions are, for example, the Quarks Lab folks in Paris. So there's this paper, if you're interested in that, be prepared for math. And with that, with these syntactically complex expressions, with the MBAs, we complete our protection. So the MBAs help us stalling out symbolic execution. Their complexity as it makes instruction removal challenging. Now, with all that complete with our protection, to wrap it up, this is a very short version of what Loki, an academic prototype, is doing towards these two design principles, so complex and target-specific instruction sets and the intertwining of multiple techniques of VM components. So in particular, we merge semantics to force a cross-handler to a global analysis. We have these polynomial encodings interlock individual instruction semantics of the handler. We have the point functions, which subvert the I/O sampling for static scenarios. And in particular, addressing design principle 1 is are the complex data flow dependent instruction semantics, and that's this semantic complexity is what makes it great to stall out program synthesis. And finally, there are these approaches to MBAs that will stop your symbolic execution attacks. So what's the impact on deobfuscation gonna be, right? So it doesn't look good, and I'd actually say we're on the limit. So it's always an arms race as with everything, right, between obfuscation and deobfuscation techniques. And right now it looks like obfuscation is winning. So the challenge is posed by adhering to these design principles, to this complex and target-specific instruction set, is that our shiny, powerful synthesis attacks don't work anymore. And recall what Tim has said before, when writing a disassembler, you don't have these meaningful mnemonics anymore. And there's not a simple add handler. There's something doing negate, add, mul, XOR, push, whatsoever. It's vastly more complex. And when we are intertwining the VM components, we force a global analysis. So before we had this very local, this handler-based analysis, and now we have a very large scope, and this makes the analysis more costly, right? And actually, this can bring us to the limitations of the binary analysis techniques and our tools. So what do we need to do to address this? So first, our analysis tools, they are our bread and butter, so we need to work on them. We need to get support for interprocedural and multi-threaded analysis. We call them multi-threaded opaque predicates. We need to account for that stuff. We need to get our tooling to work effectively and efficiently on large instruction sequences. Because we have this one basic block where we have multiple instruction semantics. We apply MBAs on them. We make them more complex. It becomes one large instruction sequence which needs to be analyzed efficiently. And an interesting avenue on how to deal with obfuscation is binary lifting. So we lift that to a higher level. We unlock the compiler optimizations or static analysis tools. And yeah, these are hard problems, not gonna lie, but we need to work on them. Two things I particularly want to highlight is first the analysis window. So this global scope. Instead of having this very local scope, we have this global scope, and this makes it difficult to analyze all of it, right? So we need to identify relevant sources and relevant things. We need to develop strategies to isolate and simplify partial data flows. So if you think back when merging the instruction semantics, we don't care about others. Maybe we want to identify one, right? And yeah, finally, we need to automatically explore the control and data flows, so we need our tooling there to get up to date. And the other concern I'd like to particularly highlight is that we need to advance our MBA deobfuscation tooling to deal with these large, especially with these polynomial MBAs. Typically, we could use synthesis to bypass all of that, but for that we need to get our synthesis approaches to work on higher semantic depths. And finally, we need our synthesis to work with constants. Constants are, maybe that's kind of surprising, but constants are hard to synthesize. There's an example for two 64-bit constants, and your synthesizer probably will not come up with them like that. All right, so with that said, let me quickly wrap up. We have seen how current VMs can be broken in a quite automated fashion. We have seen how the industry, or where the industry and also the academia in turn is moving. We have seen a couple of techniques for hardening these VM handlers and what we've done for Loki. And we have discussed how code deobfuscation research has to catch up to deal with that. And I guess it's fair to say that these next generation VMs will shape the landscape of modern obfuscation for a couple of years and probably some of your lives when analyzing them. All right, thank you very much for your attention, ladies and gentlemen.
Great talk, thank you. So I'm curious about the performance overhead when you implement all these next generation protections. How does it compare to classic VMs, and is it tunable?
Well, this obfuscation overhead is always a thing. So let's first take Temida or VM Protect. Normally, they have an overhead about 100 to 500, so in size and performance. And especially in Loki, when we designed Loki, we tried to basically be in the same level or a bit faster. The thing is, Temida and VM Protect use a lot of junk code That's just wasted space and wasted execution time. So, and we were basically aiming at keeping the similar boundaries, but creating it in a way that you just don't have to blow it away. So, but yeah, of course, this is a problem, and it mostly depends how you design those stuff. So basically, if you tweak one parameter, it will cause some others of the others. So basically, if the companies who work on that in the industry basically have to do a lot of fine-tuning and have to be aware of the overall concept and how they tune. They might have to do some size tuning. Perhaps they have to speed up some things because they don't want to use a lot of multiplications due to overhead or stuff like that. So it mainly depends how you design it exactly. So each small design decision will have an overall impact on everything.
Thanks for the talk. I just had a question about MBA synthesis, specifically if there's any considerations taken to avoid integer overflow if you start to add or subtract very large constants, or if those operations are emulated in software instead.
I didn't really get the second part of the question.
Me neither.
Yeah. Oh, did you get it? Yeah.
No, me neither, sorry.
Oh, okay. Yeah, sorry. So it was about when you start to generate these MBA synthesis, some of those operations could potentially overflow. And so I was wondering if there's any considerations in that synthesis or if all those operations are instead emulated in software. Because if you're on a fixed width does that make sense? If you're on like a fixed width instruction set, like you have 64 bits and you start to add numbers outside of those ranges.
Okay, yeah, I got it. So normally what we do is we basically OPAC predicates work by design with overflows and underflows and stuff like that. So they are always on a fixed size, like fixed size 64-bit or 32-bit or stuff like that. But still, you can have semantic downcasts and upcasts and things like that, and they will also be used and considered. So it doesn't cause any problems. But overflowing and underflowing on the same bit size is a design principle in general by MBAs.
All right, thank you very much then.
Thanks.